HIM2 is presenting tokamak toroidal field coil optimization. The system is made out of three subsystems, namely support structure subsystem, cooling subsystem, and blanket wall subsystem. The input and output of each system follows the system flow diagram. Since each system is linked with mass, coolant heat properties, and work thickness variables, the system level design was necessary. The inputs of support structure subsystem were number of boundary nodes for support truss, section area of truss members, and scale vectors and center coordinates of structure subsystem. The output was subsystem material cost. The linking variables were rate of cooling and blanket wall subsystem influencing the structure dimensions. The parameters were as followed. There were 5 design variables, namely number of boundary nodes, cross-sectional area of truss members, ground span scaling factor, angle span scaling factor, and x-coordinate of center ground node. The intermediate variables were as followed. Constraints included force equilibrium, allowable stress in truss members without buckling, lower and upper bounds. Objective function was the material cost of truss members. The trade-off was between minimizing the structural cost and satisfying the stress and buckling constraint. To define an element method assuming linear elastic material behavior was used to satisfy the force equilibrium. The problem was solved using the MATLAB genetic algorithm because the formulation was the mixed integer nonlinear optimization problem. The results showed that as the population size and number of generations increased, the objective function decreased and converged. The optimized solutions indicated that a minimum number of supports with a small but sufficient cross-sectional area can safely support the core load.
Next, looking at our cooling subsystem at a high level, which removes heat generated in the copper toroidal field coils using liquid nitrogen. The model takes in inputs, does computation, and generates outputs that are checked against key constraints. If the design is feasible, we compute the total cost, and the optimizer iteratively updates the design variables to minimize cost as shown by the objective function. Keynote, key coupling, higher temperature equals higher resistance, meaning more heat needs to be used. Our optimization is structured around parameters, fixed system conditions, design variables, what we control, intermediate variables, physics-based model computations. Next, I will pass it off to Jinro to talk more about trade-offs and the model in depth.
Our objective is to minimize the low total system cost while satisfying strict thermal and pressure constraints. It's a tug of war. To prevent the liquid nitrogen from boiling, we need a high flow rate, but that cubically increases our pumping costs. We also balance the steel's thickness for strength against the pipe's internal diameter to avoid massive friction penalties. Our physics model captures temperature-dependent Joule heating and uses the Dittus-Boelter correlation for turbulent heat transfer. Because these fluid and thermodynamics are highly nonlinear, we choose MATLAB's FMINCON with an interior point algorithm. To ensure we didn't get trapped in a local minimum, we implemented a multi-star heuristic to guarantee a true global optimum. This table shows our 5 runs, with run 5 being the global optimum. The system is highly sensitive to the nitrogen boiling point. Our best design operates just below saturation to maximize thermal efficiency. Run 3 proves that reducing pipe diameter causes a massive spike in pumping costs. Finally, using 316 stainless steel allowed us to operate at higher pressures, which safely raised the boiling point and expanded our feasible design space.
Now, let's move on to the blanket wall subsystem. The primary roles of this subsystem are thermal absorption and radiation shielding. The inputs are peak heat flux from plasma and inlet coolant temperature. The outputs are mass per module, outlet coolant temperature, and residual heat flux. The linking variable is blanket thickness, which dictates the heat loss path to the cooling subsystem and determines the mass load for the support structure subsystem. We define several parameters based on ITER standards. We choose 3 design variables to optimize: blanket thickness, coolant pipe diameter, and flow velocity of coolant. There are 3 intermediate variables: mass per module, coolant mass flow rate, and outlet coolant temperature. There are 3 constraints: mass constraint, thermal constraint, and shielding constraint. Our objective function is to minimize the total cost. And there is a trade-off between the cost and thermal safety. Reducing thickness saves cost but increases the thermal risk. There are some assumptions: steady-state heat transfer, uniform heat flux distribution, negligible pressure drop, and material properties remain constant. We use the energy balance equation and some physical limits to model. We use the SQP via MATLAB for this nonlinear constraint problem. As shown in the table, we perform 5 runs with different initial guesses. In every single run, the model consistently converged to the same minimum cost of $7.84 million. The optimal thickness always stayed at the lower bound of 0.3 meters. And the results shows that the thermal removal is the primary bottleneck of our design. To maintain safety at the minimum required thickness, the system optimized the pipe diameter and flow velocity to keep the outlet temperature exactly at the safety limit. Thank you.